Hello and welcome back. Today I want to start talking about switches and focus on the most basic type, the mechanical switch. The specific thing I want to look at is failure modes and ways in which you can prevent them. So what are the various protection circuitry commonly used with switches? And if you're curious, then keep watching. So, a while back, I built the circuit for my 3D printer. It's a set-reset flip-flop, and the idea was that if the power goes out during a long print, the printer should stay off until I'm there to restart it and reset the device. So the first normally open switch is used to turn on the supply, and when the output is at 24 volts, the relay will maintain the supply on. The second switch, which is normally closed, is used to interrupt the supply to the relay and thus the main supply, so everything turns off. This is a very basic 2-switch 1-relay circuit, and after 2 or 3 on-off cycles, both switches ended up breaking. Now, I did not intentionally make it bad, it's just that sometimes it's easy to forget about the details. So why did it break? And more importantly, how can it be prevented without compromising the functionality? Well, the first thing to understand is how do you misuse a switch to break it in the first place? Well, for this you got two main methods, over voltage and over current. Now, most mechanical switch datasheets, whether it's a basic switch or a more complex relay, will have a clearly marked voltage and current rating. This is the information that is usually also displayed on the component itself. Now, by exceeding these a little, the switch's lifespan will usually be reduced, and by exceeding these parameters a lot, the switch can be completely broken the first time. Now, a really good datasheet will also tell you that the switch can handle slightly higher values of current for short periods of time, so during inrush events. So how can you unwillingly exceed these parameters? Well, it has to do with the load that the switch is driving. So if we take a 40 volt 1 ampere rated switch, and we use a 40 volt supply and a 40 ohm load, the switch will never be out of its safe operating area. When the switch is open, there are 40 volts across its contacts, and when it's closed, there is a 1 ampere current running through it. So when driving resistive loads, it's very easy to choose the right switch if you know the supply voltage and the load value. With this information, you can always determine the exact voltage and current that the switch will see, and choose the first switch that is equal to or preferably rated above that. The problem becomes far less clear when the driven load is reactive, capacitive or inductive. So when a switch closes on a capacitive load, you will have a huge current spike, so an inrush current. This is needed to take the capacitor from 0 volts to whatever supply voltage you have. When the switch is opening, there is no issue. Current instantly drops to 0, and the voltage slowly increases as the capacitor discharges. On the other hand, when driving an inductive load, you will be getting a huge voltage spike, also known as inductive kickback, and this is occurring since the current in the inductor cannot instantaneously drop to 0, so the energy stored in the magnetic field needs to go somewhere, and the inductor turns into a reverse voltage generator. When the switch is closing, on the other hand, the voltage instantly drops to 0, and the current slowly increases as the inductor opposes the change in flow of current. Now, these two effects, the current spike with the capacitive load and the voltage spike with the inductive load, are far less easy to quantify. They are there for short periods of time, and the exact values are dictated by the exact reactances and the various resistances present in the circuit, and are just the thing to ruin your day. And in the case of my basic circuit, I have both types of load, and thus both failure modes. The AC to DC converter is a capacitive load, the input side is a rectifying bridge with a large capacitor bank, so at turn on, you get the huge inrush current. Even though there is little to no permanent resistive load, the capacitor inrush is enough to break my low current switch. My 250 volt 1 ampere rated switch got broken during the switch closing cycle. The other switch is driving a clearly inductive load, a relay. It's a 50 milliamp or so circuit, but when the switch becomes open, all of the energy in the relay coil gets turned into a high voltage spike, larger than what the switch is rated for, and again the 250 volt 1 ampere switch ended up breaking. Hopefully now the problem becomes a bit more clear. Real-life loads usually have some reactive part, either inductive or capacitive. So when designing switch circuits, it's important to keep this in mind and make sure the switch is never exposed to an out-of-spec transient. Let's now look at some protection methods, and to see how they're supposed to work, let's also simulate them. Let's start with the inductive load. So here we need to make sure that the switch will never see a voltage too high. If we run the circuit to see what happens, so based on the control signal, when the switch is opening, the inductor current cannot instantaneously drop to zero, and with no protection element, the simulator is giving us kilovolt values appearing on the load. Now in practice, an electric arc will occur over the switch that will damage its internal contacts. And we want to prevent that. So I found a few ways in which this can be addressed. And mainly, these involve giving a clearly defined path for the inductor current to go. First, we have the option of using semiconductors. So the basic flywheel diode will give the inductor current somewhere to go, and therefore the voltage present on the load will always have a very reasonable value. So when the diode is conducting, we have a small negative voltage appearing on our load. Now we can take this idea one step further and add in a Zener diode, and what this will do is create a much larger negative voltage appearing on the load, but the advantage is that the current in the load with the Zener diode will drop to zero much faster than in the case of the basic diode. So the larger the voltage drop, the faster the discharge of the current will be. Now this diode or Zener diode combinations will work very well for DC circuits, and if you have an AC circuit, then you will need back-to-back Zener diodes or TVS bidirectional diodes. So in this case, where we have a sine wave supply voltage, when the switch is transitioning, we have the same inverse voltages appearing. So on the first transition, the voltage will drop to negative values. On the second transition, it goes to positive values, but the exact amplitudes are always controlled by the Zener diodes. Now, if you don't like semiconductors, you always have the option of using passives. And here, the most basic version involves using a permanent resistive load. So whatever current was running through the inductor, this needs to drop to zero, so in this case it's 100 milliamps. So if we add in a 1 kilo ohm load, the inverse voltage will be limited to 100 volts. So this will be the voltage that occurs when you pass the 100 milliamps through the 1 kilo ohm resistor. You can get smaller voltages, but then you need a larger permanent load. And well, you don't really want to have permanent loads added into your circuit. So the next best thing is to only connect your extra resistor when a transient is occurring. So during your steady-state DC operation, you don't want to have this load connected. So to achieve this, you can connect it through a capacitor. So with the second circuit, this RC version, we are able to absorb the inductor current into our resistor through a capacitor. And this way, we no longer get our large negative spike. The only drawback here is that again the inductor current doesn't instantly drop to zero, but it takes the time it takes, so based on the values of the RC circuitry. Finally, we have the option of a varistor. So this is a 2-terminal voltage-dependent resistor. It only has 4 terminals in this simulator. And what this component does is that above a certain voltage, it starts to conduct current. So it's behaving similarly to the bidirectional Zener diodes. And again, this will allow a certain negative voltage, but it will be clamping in both directions. And in general, out of all of these 6 methods, only the first 2 are specifically for DC circuits. All of the other ones can be used on AC signals. These methods will work really well when they can be placed close to the inductive load, or when the switch is close to the supply and you can add the protective elements there. It's worth noting though that in some use cases, the load and the switch can be quite far apart, and here the wires themselves can become part of the inductive problem. And if the switch is not necessarily close to the supply, you will also get some inductance on that side as well. So with this sort of setup, you have an inductive load on both sides of the switch. Then what do you do? So with this sort of setup, where you have considerable wire inductance on both sides of the switch, you can have a problem even if your final load is resistive. So in this case, rather than trying to suppress the spikes appearing over the load, or well, the wire, it's far more practical to try to limit the voltage that can appear on the switch. So with this setup, the switch is getting exposed to kilovolt level spikes again during the opening phase. So to counteract this problem, I found three main ways. The first method involves using a basic capacitor over the switch terminals. So by doing this, the switch never gets exposed to very high voltages because any transients generated by the inductors will get absorbed by this capacitor. The only downside, of course, is that when the switch is closing, it will be exposed to very high currents since it's basically short-circuiting the capacitor. So the obvious way to counteract this is to add in a series resistor. By doing this, the switch will get exposed to some small voltage spikes, but at least you will no longer have overcurrent problems. So the exact value of the voltage spike and the current running through the switch will be determined by the two component values. In the end, you want to have a smallest possible resistor to minimize the voltage, but you also want to have a largest possible resistor to limit the current. So designing this component will be a compromise between the two effects. To address this, the final thing that you can do is add a diode into the mix. So the idea here is that when the switch is opening, the inductive current needs to go directly into the capacitor, so through this diode, but when the switch is closing, the capacitor is shorted through the resistor. So if we look at the behavior, we see no voltage spikes appearing, and if we look at the current, well, we do see a spike, but this is more or less a simulation error, since the spike is in the picosecond range. So when the switch is closing, the diode is blocking, so the capacitor gets discharged through the large resistor. Here we should also mention that the capacitor and capacitor resistor versions of the circuit work for both AC and DC circuitry, but the resistor capacitor diode circuit is a DC only circuit. So this covers the main ways in which a switch can be protected when it's driving inductive loads. You can have other components involved, but these are the basic principles. Next, we have the topic of capacitive loads. Here we have a bit of a problem. The common practical way of limiting the inrush current is by adding resistance. So with absolutely no protection, the current will only be limited by the switch's internal resistance, the wire resistance, the supply's internal resistance, and any resistance present in the load in series with the capacitance. If this is not enough, you need to add some more resistance. So by adding this resistance, this will of course limit the inrush current, but it will also drop the voltage that reaches the load, and it will constantly dissipate some power. This is sometimes acceptable. In low current high voltage circuits like phone chargers, you will see this sort of resistors in series with the power line for the purpose of limiting inrush. But if you want a better behavior, there are two main countermeasures that I've found. Instead of using a basic resistor, you can use an NTC type thermistor. So this component will have a large resistance value when it's cold, limiting the inrush, but as the circuit runs, it will heat up and the resistance drops, lowering the losses. This is a good solution as long as the time it takes for the capacitor to discharge during turn-off is similar to the cooling period of the NTC thermistor. Otherwise, a set of fast turn-on, turn-off cycles could get you to have a hot thermistor and a discharge capacitor, which is not good since you would be losing the current limiting benefits. The other, more complex way involves using a relay to shunt the resistor after the output voltage reached a certain value. This way you remove the permanent resistive loss, but you need to keep the relay active. This is worth doing when the energy required by the relay is far smaller than what would be wasted on the resistor. And depending on the use case, you may also want to add in a time delay circuitry that activates the relay only after the load reached a certain value and a certain amount of time has passed. In the end, there are multiple ways of protecting switches, based on the exact use case that you have. The exact method needs to take into account not just the switch at hand, but also the load, the total cost of the final system, and the exact performance that you need. Now, before showing you how I ended up fixing my circuit, I will be trying out some of these methods in real life. But that is the topic for next time. For now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be updated on my videos, and see you next time. Bye bye.